My name is Christopher Ye, and I just finished the second year of my PhD at Caltech in the Department of Computing and Mathematical Sciences. Along with my collaborators Jing at Caltech and Yuanyuan at UCSD, and my advisor Adam Wierman, I developed a novel algorithm for robust online voltage control on an unknown grid topology. I'd like to highlight that while the novel control algorithm here is demonstrated on the voltage control problem, the principles behind the algorithm are widely applicable to a general class of nonlinear online robust control problems.
As you may know, the world is seeing increased adoption of renewable and especially solar generation. Indeed, the plot on the left shows annual solar generation in the USA from 2010 to 2021, and we see a rapidly increasing trend. However, a major challenge with renewable energy sources like solar and wind is that we have no control over them, so we can only rely on imperfect forecasts. Furthermore, they tend to have high variance. On the right, I've plotted the electricity demand and solar generation for a full day from part of the Southern California electricity distribution grid. The net load that the utility company needs to supply electricity for is electricity demand minus renewable generation. Note that this net load has greater fluctuation than the electricity demand itself. In other words, adding renewables tends to increase the variation and unpredictability of net electricity load.
In this paper, we specifically consider distribution grids, the part of the electric grid that brings electricity to homes and buildings. We can think of a distribution grid as a graph, with nodes, also called buses, representing, for example, buildings, and edges representing power lines. Especially as homes and commercial buildings adopt rooftop solar, solar penetration is increasing. Voltages in distribution grids must be maintained at near constant levels to ensure grid stability. Maintaining the voltage within certain voltage limits is known as the voltage control problem. However, the large variance and unpredictability of solar generation relative to typical loads or demand brings a significant challenge to grid operators who seek to maintain voltages within these limits. Without applying any sort of controller to a distribution grid, it is likely for the voltages to exceed the regulatory limits. Here I've plotted the voltages for one day at two nodes in a toy distribution grid. The dashed lines denote the voltage limits at 5% deviation from the nominal 12 kilovolt voltage. Due to the large fluctuations of solar generation throughout the day, the voltages at the two plotted buses exceed the voltage limits. And because all nodes are connected through the network structure, even voltages at nodes without solar generation may be affected by fluctuations in solar generation. So what can an electric utility company do to avoid exceeding the voltage limits? As I alluded to earlier, this is the role of voltage control. The goal of a voltage controller is to decide on power injection values at each bus within a grid to ensure that the voltages stay within fixed limits. Because a distribution grid is a connected network, power injection at any bus will affect voltages everywhere throughout the network. Therefore, most controllers rely on knowing the complete grid topology and line impedances in order to decide on the control action. However, the exact grid topology and line impedance values are in fact often unknown to the grid operator. There are several reasons for this. First, many distribution grids are automatically reconfigured up to several times a day, depending on generation and load conditions. Second, lines may be reconfigured during periods of maintenance or to respond to downed power lines. Additionally, temperature fluctuations throughout the day may have a significant impact on the line impedances between buses. And finally, many grid operators simply have outdated or incomplete information about their grid layout. We have personal experience with this issue here at Caltech and with the local Pasadena water and power utility. All of these factors introduce uncertainty about the network, presenting a major challenge for voltage controllers that often assume exact knowledge about the network.
Even though the network is often unknown, we can generally assume that distribution networks are radial, that is, they are tree-structured. So, for a given set of buses in the distribution grid, the network may look like this, or this, or this. So what are the existing approaches to voltage control, given all of the network uncertainty? Generally speaking, there are two strategies that are commonly adopted. The first approach is to estimate the grid topology and line parameters, then apply traditional control methods. However, these methods often require making strong statistical assumptions on the noise and distribution of voltage measurements, which may not always reflect real-world settings. And in the case that the learned network is imperfect, applying traditional control methods on the wrong network may lead to even worse voltage violations. The second approach is to use a network-agnostic controller. Many of these controllers are decentralized, making only local adjustments at each bus. However, because they do not take the full network information into account, under realistic assumptions, they generally do not provide guarantees on their ability to stabilize the voltage, resulting in some voltage deviations. As existing approaches have significant limitations, we propose a novel technique for voltage control on an unknown distribution grid network, with stability guarantees under realistic assumptions. The approach that we take is combining simultaneous learning and control by pairing consistent model chasing with robust control. In the next slides, I will go into detail about how this is done. Before diving into the details, though, I would like to highlight two major takeaways about our approach. First, our approach does not require learning the exact network. We only learn just enough information about the network to perform robust control. Second, even though we demonstrate our simultaneous learning and control approach on this voltage control problem, the underlying ideas are widely applicable beyond voltage control. Now, I will introduce the dynamical system describing voltages in a radial distribution grid. Under the assumption that the distribution grid has a radial tree-structured topology, we can linearize the dynamics to arrive at the system shown here. The squared voltage magnitude at each bus is a linear function of the reactive power injection, Qt, which is the control input, as well as the noise, V partial of t, which includes electricity demand or load. The model, X star, depends on the grid topology and line impedances. In our setting, the model X star is the unknown value because we do not know the grid topology. We make four reasonable assumptions about these voltage dynamics. First, the unknown model, X star, lies in some known uncertainty set, calligraphic X. This assumption requires some knowledge from the electrical utility to determine what the initial uncertainty set is. Second, we assume that the noise is bounded. Specifically, the noise lies within a known compact convex set denoted capital V par. This is a necessary assumption because if the noise could be unbounded, then there would be no hope of performing voltage control. Third, we assume that the change in noise between time steps, denoted delta V par t, is bounded by a positive constant eta. This assumption is reasonable because electricity demand generally does not change too erratically. Finally, we assume that the control input Q is bounded, but that the bounds on the control input are sufficient to handle all possible noise and all possible models in our initial uncertainty set. Given these voltage dynamics, we can now present a high-level algorithm for voltage control. First, since the true model X star is unknown, we start with an initial guess. Then, at each time step, we do the following. Based on our guess X hat of t, we decide on a reactive power injection Q of t. This is our control action. The amount of reactive power injection, though, must be within a limited range. Then, the voltage at the next time step is determined according to the dynamics shown on the previous slide. We can add our chosen reactive power injection, Q of t, and the observed voltage, Vt plus 1, to a data set of historical observations. Finally, we update our guess to be consistent with the observed data. In a moment, I will explain what I mean by consistent. This procedure repeats for each time step, and our objective is to maintain the voltage within a pair of given voltage limits. There are two key steps in this algorithm. I will first discuss how we use our accumulated data set to approximately learn the unknown model via consistent model chasing. Later, I will mention how we borrow ideas from robust control for picking a reactive power injection point based on our guess of the model. Consistent model chasing effectively asks the question, what possible models X could have generated the observed data d of t. We call this set of possible models the consistent set at time t, denoted p sub t. Every part of this consistent set definition follows directly from the three assumptions I introduced earlier. First, a consistent model must lie within the initial uncertainty set. Second, the noise is bounded. And third, the change in noise is also bounded. If some model X violates any of these conditions, then we know it could not possibly be the correct model. And at every time step, we observe more data. Since each observation introduces additional constraints, the consistent set shrinks over time. We can show this process in pictures. The initial consistent set is our known uncertainty set. We know that the true model X star lies somewhere in this set, but we do not know where. Because we have to perform control, we make an initial guess, X hat 1, within the initial consistent set. Based on this model estimate, we decide on a reactive power injection, and we observe a new voltage. This new observation imposes some constraints on what the consistent models could be. These constraints are hyperplanes that shrink the set of consistent models. In this figure, we see that X hat 1 is not consistent with the observation, so we make a new guess, X hat 2, that is consistent with our observed data. Again, we use the new model estimate, X hat 2, to decide on a reactive power injection, and we observe a new voltage. This observation imposes a new set of constraints. We see that X hat 2 is no longer consistent with our observed data, and we make another guess, X hat 3, that is consistent with our observed data. This process continues on and on, with the consistent set shrinking over time towards the true model X star. Notice that the consistent sets are nested and always convex. Thus, we have reduced the problem of learning the model to the problem of nested convex body chasing, which is a well-studied online learning problem with many existing algorithms. Now that we have a method for learning the model, how does this provide any guarantees against violating the voltage limits? Well, this is where robust control comes in. For each model guess, we design a controller specific to that model. By a controller, I mean a function pi that maps the current voltage to a control action. So, given the initial model guess X hat 1, we have a controller pi of X hat 1 that takes as input the initial voltage V0 and determines the next reactive power injection Q of 1. We are able to design this controller with the guarantee that if all future data is consistent with that model, then voltages will stay within limits. In fact, we are actually able to design a controller with an even stronger guarantee called row robustness. For each model guess, our controller guarantees that if all future data is consistent with any model within a radius row ball around our model guess, then voltages will stay within limits. The value of rho depends on the sufficient control assumption, and this controller is based on solving a convex optimization problem, the details of which I encourage you to read in our paper. For now, let me explain why row robustness is important. Because we have a row robust controller, if the first data constraint does not completely eliminate the row radius ball around our first model guess, then notice how the green region from the consistent set is still within the row radius ball. Thus, there exists some model within the row radius ball that is consistent with the data, so our controller will not violate the voltage limits. Thus, we have no reason to update our model guess. Only if we observe more data that shrinks the consistent set to completely eliminate the row radius ball is it possible that the controller may cause a voltage limit violation. Then, we would obviously make a new model guess. This leads to the key observation underlying our entire algorithm. every voltage limits violation causes the consistent set to shrink by at least the size of a row radius ball. Since the initial uncertainty set is compact, that is, closed and bounded, it has finite volume. Therefore, there can only be a finite number of voltage violations before we have eliminated all uncertainty from the model. I now formally present our main result, which is a finite mistake bound for our voltage controller. Specifically, our algorithm ensures that the total number of voltage limit violations, which we call mistakes, is at most 4 times gamma over rho, times the diameter of the initial uncertainty set. Gamma is the competitive ratio of the particular nested convex body chasing algorithm used for consistent model chasing. It is also a function of the number of nodes in the distribution grid. The state-of-the-art nested convex body chasing algorithm is based on the so-called Steiner point, which achieves the optimal competitive ratio of m over 2. However, to date, we are not aware of any computationally efficient method for computing Steiner points in high dimension, as in our case. Thus, in our experiments, we instead use a projection algorithm that projects the previous model estimate onto each new consistent set. Its theoretical competitive ratio is much worse, but empirically, we show that it still performs well. To the best of our knowledge, this is the first such finite mistake guarantee for online voltage control on an unknown distribution grid topology. And again, unlike previous approaches, our algorithm only learns an approximation x hat of the true model x star. Now that I've presented our theoretical contributions, how well do we avoid voltage limit violations in practice? For our experiments, we tested our algorithm on this single-phase 56-bus network from the Southern California Edison utility. We artificially adjust the net load at many of the buses as if they had solar panels. We use 24 hours of data sampled at 6-second intervals. And for the initial uncertainty set, we use a ball around the true model. For more details on our experimental setup, please see our paper. Here, I have plotted the voltages over time from 2 buses. I've chosen these 2 buses for plotting because without a controller, they exhibit some of the worst voltage violations. We start with an incorrect initial model guess. In blue, I plot what happens if we apply just the row-robust controller to this incorrect model without performing consistent model chasing. Using this incorrect model actually leads to large voltage oscillations, which is why the blue curve looks like a blob of blue. Clearly, the controller fails to stabilize the voltage under the incorrect model. However, if we use consistent model chasing to update the model estimate over time, we get the curve shown in orange. We see that the voltage is nicely stabilized and maintained within voltage limits. In fact, we can really see that learning the exact model is unnecessary. The plot on the left shows how close our learned model gets to the true model over time. The norm of the difference starts above 80, and over time it shrinks to under 50. Note, however, that it does not go to 0. We can also examine how important learning the true model actually is. In purple, I've plotted the voltage when we use the row-robust controller given the true model. The orange curve shows the voltage with our algorithm learning the model online. We can see that the voltages from our algorithm do not differ significantly from using the true model. That is, using an inexact learned model performs similarly to using the true model itself, again demonstrating that learning the exact model is unnecessary. We also tested our model with varying amounts of initial model uncertainty. For this set of experiments, I increased the diameter of the uncertainty set, and you can see that the initial model error is much larger than before, over 120 here versus only about 80 in the previous slide. As before, using the wrong initial model in blue results in large voltage violations, whereas our algorithm in orange makes some mistakes but quickly learns and corrects for these violations. In practice, we may not always have the ability to observe voltages at all buses. So what if we only have partial observations? We consider the same large uncertainty set as in the previous slide, but we withhold voltage observations from 7 of the 56 buses, including the 2 buses shown here. The results are shown in green. We see that withholding observations from 7 buses does not change the model estimate that much, and therefore the voltages are also similar to the fully observed case. Finally, how does our algorithm compare to existing algorithms? We've chosen to compare our algorithm against 2 model-agnostic controllers shown in blue. These controllers are decentralized, making local adjustments to the reactive power injection at each bus without taking into account any of the distribution grid topology information. These decentralized controllers have been theoretically proven to stabilize voltages if the voltage controller has an unbounded range of reactive power injection capability. In the real world, this assumption is clearly invalid, as the actual range of reactive power injection at each bus is fairly limited. Under the more realistic bounded control assumption, these decentralized controllers result in large voltage limit violations. In contrast, our algorithm in orange performs well. In conclusion, we have presented the first online voltage control algorithm under unknown topology with a finite mistake guarantee. Notably, our algorithm does not require learning the exact model. Our experiments confirm that our algorithm is robust to uncertainty in the distribution grid model, even under partial observations. We again emphasize that our approach of combining consistent model chasing with a robust online controller is generalizable to other online nonlinear control problems. Finally, there are many possible directions of future research, from considering settings with only partial control to handling uncertainties in the measurements themselves and more efficient implementations of the consistent model chasing component. Thank you for taking the time to attend this presentation. I encourage you to read our paper for more details and to check out our code on GitHub.